Okay, so for problem number 6, we did this in class, but in case you were absent or need just another run through, we are going to start with the fact that the circuit, the switch is closed for a long time. So if this switch is closed, then our current's going to start at the battery. It's going to move through resistor 1, the inductor, and then it's going to bypass resistor 2 and back into the negative side of the battery. So what is the current in the circuit? So what we know is that the current starts at 0 and it increases till it reaches steady state. And after a long period of time, we can think of our inductor as just a wire. I can draw it like this, just a wire like that. And then at that point, we've got just one resistor and one battery, which gives me an EMF, a current of EMF over R1. So that's going to be our answer here. And then after being closed for a long time, we've got a buildup of charges here in our circuit. The switch is reopened, so let's erase that there. And now our current, I might as well continue, is going to run through R2 and to the battery because that is now our closed loop. So the current in the circuit after the switch has been opened for a long time means again that our current is going to go in this pattern. The inductor is even when the switch is open, is going to resist change. So it's going to want the current to continue in the same state. And we're going to draw the graph for this. But the current initially is going to be the current it ended at when the switch was closed. So that's going to be the starting state. We're going to draw the graph for part C, so I'm not going to do that now. But we now want to determine the current in the circuit after the switch is open for a long time. So as I stated, the wire after a long time is the inductor is treated as a wire after a long time. But this time we've got the closed loop going through resistor 1 and resistor 2, and they are in series. They are within the same loop. So now our equivalent resistance is R1 plus R2, and our our current is EMF over R1 plus R2. I started drawing the graph for C, so I'm just going to continue that drawing over here. I start off with the current that I ended at, EMF over R1. I end after a long period of time at EMF over R1 plus R2. Now, that's the point in which it reaches steady state. So I'm going to start here, and it's not necessarily discharging, but the higher resistance causes the current to decrease until it reaches steady state. And so that's the shape that you're going to create once the switch is open. The next question, and I'm going to do all the work up here because I drew my graph there, is to apply Kirchhoff's loop rule and write the equation to relate potential difference around the circuit. So we're using Kirchhoff's loop rule through this loop. I'm going to create my Kirchhoff's loop, which goes in, generally you want the loop to go in the direction of the conventional current. And we start at out of the positive side of the battery minus the voltage through resistor 1, so IR1, through our inductor. So we still want to consider the inductor when we are working with our Kirchhoff's loop. So that's going to be minus L di dr over dt. And then we're going to continue through resistor 2, which has a negative voltage drop, and then back to the battery. So this Kirchhoff's loop rule, sorry, this should be 2, is equal to 0. I'm going to simplify it down. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . to this. And then we're going to use this to solve for E. Now, E is pretty difficult, so I don't actually expect you to have to do this on a quiz or a test or an AP exam, but we're going to do kind of the same process we did in problem number 5, where we're deriving an equation. So here's the question. Find the equation for the current as a function of time. It's not a single RC circuit with one resistor, or sorry, RL circuit with one resistor and one inductor. So the process is going to be a little bit more difficult. So I'll show you up to the point where we integrate, and then I'm going to stop there. And most of the time you're going to do an integration more like problem number 5. So here, what you want to do for part E is you want to bring our di dt, because we're solving for the current with respect to time, where our I variables are on the right and our t variables are on the left. So I'm going to start by doing this, and then divide the L. So I know this seems like a strange step, but I am going to multiply top and bottom by 1 over R1 plus R2. And that gives me EMF over R1 plus R2 minus I, so I can get I by itself, over L over R1 plus R2. And then I am going to divide this to the other side. And then in the end, I can switch this to its reciprocal. And then from there, we can multiply dt. So the left side is a constant that I can integrate. The right side is going to be this crazy integration here. So I can integrate this. Actually, I'll integrate here because this is constant, 0 to time t. And then I integrate here from our starting EMF, which is EMF over R1, to some arbitrary current. And obviously, we're going to have to use substitution. So again, the math here is more complicated than what you would be expected to do on an AP exam. The process of trying to get the variables for current and the variables for time into opposite sides of the equation and integrating is a concept that you want to know. But it's going to be much more similar to, oh, I already erased it, but much more similar to the type of integration we did for problem number 5.